is 3 o'clock according to Tim Cook, so that's you go with. So I'm pleased to introduce David Fisher from Rice University. He is the Milton B. Porter Professor of Mathematics at Columbia and PhD in 1999 from the University of Chicago. He's going to be telling us about hidden applications of hidden symmetries. I'm guessing there might be a hidden agenda here as well. So take it away.
There is the hidden agenda, but we'll find out. I do want to thank the organizers for organizing this workshop and inviting me to TCU. I'm happy to be in the neighborhood, happy to be in Texas. And I didn't realize until I got here that one of my favorite colors is TCU colors, so that's just another good reason. I also want to thank the other speakers for giving. Been a lovely conference with just a lovely broad array of talks about very different topics. And this will be yet another very different topic than the others. And so to start with, I want to start with a very old but very elementary problem. They take two matrices. First matrix is going to be that one. Second matrix is going to depend on a parameter. Parameter I'll label S, that one. I'm going to look at the, these are, A and B are elements of, well, let's have it be SL2 of, you can think real coefficients that make S real. You can think complex coefficients if you prefer to. Most of the things I'll say are open in many cases either way. And you can now just think of this as two matrices generate some subgroup of SL2R, so this generates a group. And you can ask, when is gamma S a free group? And we really want freely generated by A and BS. It's a technical difference that you shouldn't worry about too much. But just one of these two matrices generate a free group. You might wonder, well, why would one pick those two matrices? Well, it's not my fault for this very own problem. The other reason you would pick those two matrices is if you look at, you have some geometry, right? If you look at the hyperbolic plane, you pick 2 points in infinity, and you look at the group elements that stabilize each of these points in infinity, this generates a nice discrete subgroup of the stabilizer at that point. This generates nice discrete subgroup of the stabilizer at that point. These are, it turns out that any, this is just sort of a normal form for a group generated by non-commuting parabolics. Two matrices chosen at random. Take two parabolic elements that don't commute. If they commute, they have the same fixed point in infinity. Assume they don't commute. What kind of group does that generate? First thing you could ask, is it a free group? First person that asked this question that I know of in the literature was Sonov in 1955, who proved that if the absolute value of S was at least 4, then this is our question. So then yes. And he did this by a technique that I will not go into right now, but I will mention again later. It's called ping pong. It's a basic way to say that you're a geometric group theorist, or in several areas of geometry and topology, you've played ping pong at some point to show that the group is free. It's sort of almost the only way we know how to show that the group is free. And maybe I'll explain it later. I don't want to right now. And then there's a pretty easy application for this, that then if S is transcendental, also yes. And easy implication if you know a little bit of algebraic geometry. The set of points where that, or the set of values of S where the thing is free is somehow a complement of a subvariety. And once you know it's a complement of a subvariety, and it's a complement of a subvariety of R, then it meets all the transcendentals. And so Samos knew that in 1955. Now, odd collection of people thought about this problem, not in about how much this 1960 proved if you're in the other setting, if S is less than 4 and not an integer, then gamma S is not discrete. And this is bad news if you like geometry and topology or dynamics or anything else, because when gamma S is discrete, you can think, oh, I have these two matrices, I can mod out the hyperbolic plane by the group they generate. I have a nice object with some kind of manifold. I can study it. If it's not discrete, if I mod out, I get something that's not got any structure at all. It's a horrible object. And so he said, oh, if you want to resolve this question in general, you're in trouble if it's on an integer. The discrete case is due to Abel in an odd sense that somewhere close to 2000, Ian wrote a blog post, right? There are only 3 groups we're talking about, because when S is 1, this is the group SL2Z, which we all understood classically, and so there's just S is 2 and 3. Those 2 groups, Ian wrote a blog post explaining why you don't get free groups. I really need to write this down in my notes and look it up more often. But it turns out Ian's blog post was maybe a little quick. This was when Ian had a blog that was just posting like 3-page PDFs because the blogs didn't actually exist in the early 2000s. And eventually there's a 60-page paper in geometry that kept the Dakota that expanded Ian's 3-page blog post into a complete argument for those 2 cases, and has 7 authors, which is why I can never remember who the authors are, because there's 7. So blog post was maybe a little quick, but they still credit Ian for all the ideas. So I will too.
Does that include the -1 and -2 case?
Yes, it includes those.
Okay.
But it's easy to see that it's the same thing because we're generating as a group. So flipping the sign is just flipping the generator to its inverse.
Okay.
And maybe I'll go over here. Just have a few more things to say at this level. And London and Ullman in about 1969 asked the following question. They just wanted to specialize a bit. If the book has to be in Q intersected with this interval from -4, 4, not integral, they really asked, can gamma S be free? And the way they ask it, they kind of hint that they think the answer is no, but they don't conjecture anything. And it actually was hinted earlier by, I think it was Hirsch, hinted this earlier in a math SciNet review. Reviewing somebody else's paper, he hinted that he thought the answer to this was no. And then Koberta and Kim, I'm not even sure this is published yet, but in about 2018, they conjecture no on this Linden-Ullman question. And they prove it for many examples. And their proofs are complicated, combinatorial, and computers. But they designed a method to make this into a computer checkable problem. If you fix parameters, they checked it in many instances. They then managed to prove it in, not just, the computer's only going to ever prove finitely many instances. If you're doing a real computer proof, they can prove it in countably many instances. Of course, they're, how big is their countable set compared to this countable set? It's pretty sparse looking from any intuitive point of view.
Maybe a dumb question. So when you say it's not discrete, it has limit points, it has.
It turns out that once, it's just write this on the board because it's a good question. The fact is that if gamma S is not discrete, then it's dense.
Hmm.
It doesn't just have limit points, it's everywhere. And that again, if you know a little bit of algebraic topology, isn't very much. But not algebraic topology, algebraic geometry isn't hard. It's just the Zariski closure has to be everything, and it's very easy to see that it's dense. Yeah, so this is actually a dense group in all these cases by natural result. And like I said, the group being indiscrete is inconvenient because it sort of nullifies most of our tools for proving anything. And so we want to make it discrete. And there's a trick for this. So we'll just write S equals A over B. And I want to write my fractions in reduced form and not upset my nieces in middle school. And also make my own life easier. And then if I write B as a product of some number of primes, what I can do is I can take gamma S and bed it diagonally and I've so far been thinking about it as living in SL2R, but that's just a bias. It also lives in SL2 QP1 times SL2 up to SL2 of QPK. And I'm not making too many people deeply unhappy by talking about the p-adic numbers. I have no idea how many people like the p-adic numbers. What's the point? Well, the main point is that this is discrete. And why is that true? The p-adic norm is just designed to make 1 over p to the n large. That's its entire purpose. It just makes 1 over p to the n really big. And so how can matrices with values just in the ring generated by S and the integers get small? They can only get small by having 1 over p to the n's in the matrix entries, and those get big over here. And that's why this thing becomes discrete. So that group now sits discretely in there, and you think, oh, good. I have some techniques and tools back, and I might be able to think about this. And if you're too much of a geometric topologist, you might think, good, p-adic groups, what's that? And not like it, but SL2R is the isometry group of the hyperbolic 2 space. Well, I should really put a P here. And SL2QP, maybe I should put a P there too, sits in the isometry group of a nice hyperbolic space too, where this is the P+1 regular tree. So if you want to know why I think this is better, I've made it discrete. The quotient is a reasonable object. It's a quotient of a reasonable object. It's a hyperbolic plane crossed with some number of nice looking trees. So this seems like something we could work with again. Turns out to be not so clear how to work with that either. I want to tell you a few more things about it before I tell you the disappointing news at that level. I will warn you. At one point, I thought I could prove this conjecture. Maybe at like 6 points in the last 3 years, I thought I could prove this conjecture. Like an element in the Faraday camp. I can't today, so I won't tell you I can today. Yeah, but I can say a few interesting things about it and prove a few related things. Now I can look at there's a projection. Let's kind of relabel this. Numbering that I picked G0 times up to GK. 0 just because that first one is a real Lie group, and so maybe you think it's special, maybe I think it's special. So I can look at pi I, the projection from G0 across GK onto the I factor. I'm only half joking calling these exercises. It really depends on your background, if they are or not. Turns out pi I of gamma S is dense. The only one of those that's really not an exercise is the one that's I equals 0 that's due to NAP. Although if you actually look at NAP paper, it's kind of unreadable and incomprehensible. And once you figure it out, you realize it's not that hard. It's, you know, he does it naively. I would do it using machine. But he does do it naively, and you can do it naively. An exercise 2 is a slightly harder problem. That is kind of what we really want to know, but it doesn't. I'll be vague about these things throughout the talk soon. I can look at the projection on not just one factor, but some collection of some factors, which is of course only interesting if I get at least one of them. This is dense in GI1. That's supposed to be 1 times up to GI, let's say J, as long as, I guess the way to say this is J is less than or equal to K.
So that's in the p-adic topology, right?
Yeah, in the p-adic topology and the p-adic. You should not worry too much about that being any different from the real topology and the real factors. You can worry about it, but you really shouldn't. It's not that different, I think. So this group is dense in all of these places.
But wait, I thought you said it's discrete.
It's discrete in the full product, but if I give up any single factor, it becomes dense. That's the
I
point.
see,
It's
I see.
discrete in this product. If you erase one factor, it's dense everywhere else.
Okay.
So I've somehow picked the minimal place in which it's discrete.
But why is it people that still become
What?
why is it that I can't get this intuition? If people that still become large.
P to the M becomes large, but well, two things to think about. One is it contains the integer points. The integer points are dense in the p-adic integers. And so you've got a dense group in sort of the you know, in sort of a bounded set, you're already dense, and then you have something big moving your bounded set around. You know, that's not quite a proof, but one can make something like that. So it really, you know, it's not just that I have this 1 over p to the n, but I also have all the integers. 1 over p to the n gets big. I should have been moving the boards instead of erasing things. I erased my 2 matrices. Maybe I'll put them back here and then move the boards up. 1 over p to the n gets small, but p to the n gets big. After all, if I take this thing to a big power, what I get is p to the n in this entry, and that gets very small pi. I checked before I started talking. Boards move very smoothly and easily, and I erased a board without thinking. I want to tell you a surprising fact that right now is just nothing more than a surprising fact. I don't have proof that it's true. It's just what we know currently. The only discrete group containing gamma S with all projections dense in the way I just described. Well, the only discrete groups, because there really are infinitely many of them, but they're all sort of the same, are finite index subgroups of what I get when I just take SL2R. Not SL2R, I take SL2 of the integers, and I just take the full ring of what I get when I adjoin these K primes. That's the only, the only way I can get something that contains gamma S right now, not a question mark, that's what's known right now. And this one, I learned this or found this out. It's not something that, because it's a statement about all known examples, it's not really in the literature. These groups are very special. And the fact that I take the full group of matrices in that big ring is very, very large group of matrices. If these two guys actually generate a finite index subgroup in here, lots of people are going to be surprised. But I begin to believe they might at the moment. Ask me again next week, and I might believe they don't again. And let's just maybe some facts about these groups. You know, this thing, these groups.
So is this known for sure or not yet?
No, this is the only discrete groups. Yeah, I wrote it wrong. The only known.
Okay.
It might be true. It really, when I first started thinking about this, I would have told you preposterous that this could be true. Right now, I think it really could be true. And these groups, let's call this group. Let's call it. Yeah, all these groups lambda. You know, it depends on the choice of times. For my notation, these groups lambda, they're called S arithmetic lattices. And they have a bunch of properties. I think every property I'm going to be listing is due to Margulis in the end. And it doesn't matter if I take the full group or a finite index subgroup. You know, two properties that we know about them. One is that if I look at lambda modest commutator subgroup, this is finite. So let's correct this. Lambda is sitting in here at finite index. And in fact, more than that's known. All normal subgroups are in fact finite or finite index. And these two things are theorems of Margulis. There are special cases of theorems of Margulis from 1978. So these properties are really not properties of groups. So gamma x is really one of these lambdas, then Kim and Roberta are really, really right. Because these groups are really, really not free. But I don't think, you know, Kim and Roberta had any sense when they wrote their history of this might. And you know, as I said, ask me today, and I believe this is probably true. Ask me on a different day of the week, and I might believe something else. And this is actually just one instance of a different sort of general question that has many other applications. You know, so you know, maybe I should say something now about the planet life. I told you about this very old problem due to Linden and Ullman. I'm going to tell you about a few other problems, and I'm going to relate these problems to hidden symmetries and say a few things I know about hidden symmetries at the end. And then maybe at the very end, tell you a few more reasons why I believe enough things about hidden symmetries that makes me think that it might go be the case that this group is actually this group. Hope to get through all of that. We'll see what happens. Here's a general question. That's sort of a variant on this that I wouldn't have asked even say 4 or 5 years ago, but now I think is a reasonable question. It says, you know, let's just take, what I want them to be. Take G0, G1 up to GK, real or kinetic, simple Lie groups. So for now, you're allowed to take all of the G's to SL2s. You're just looking at a copy of K copies of the isometry group of the hyperbolic plane that might make the geometers in the room to think of that case. And consider gamma a subgroup of G0 cross up to GK with all what I'll call subfactor projections dense is gamma a lattice. And the product. I.e. is the volume of, I forgot to give this guy a name, call the product G, is G mod gamma of finite volume. And I should say that, like, if you don't like manifolds of finite volume, and you prefer compact manifolds, you just assume I say compact there. You don't lose a lot of intuition or anything in this part of the world if you do that. And this is very much put a period at the end of it. That should be a question. And as I said, if you asked me this question, I think even 2017 or 18, I would have laughed at you. Because I would assume someone knew counter. I'll tell you a special case of this where I assume someone knew counter examples. You could assume that you don't. It's reasonable to assume gamma's finite. You want to do that here, it's okay. There'll be related problem later, where it won't be over. But for now, it's okay. So the special case, sadly, the club of hyperbology, people who like hyperbology, I'm happy. I'm gonna go back to trees for a while because the tree case is somehow the one that first interested me in related problems. Just think for a minute about the special case, and it has a lot of application. Special cases, SL2, P. You can ask all the questions you like.
You just take a G times P and then take a diagonal bed. And then you forget.
No, if you take it, it depends on what you mean. So if I take gamma and I embed it in G times G, if it's discrete, if it's this, say G1 equals G2. They have same group twice. I take some subgroup of the group and I embed it back. If that group is discrete, it stays discrete. If it's densely attractive, it stays dense. And really there's some sort of you always want to take sort of the minimal setup. The minimal setup is when I'm discrete in the product, but all my subfactor projections are dense. And you're right that I left out a word here, which is I want gamma to be discrete. Thank you. I confused my apologies. I want it to be discrete in the product, but project densely everywhere. And sort of looking at the minimal setup in which it's discrete, you might call that the irreducible setup. That word hasn't been defined in the literature yet in this level of generality, but special case is this one. This is two trees, a p plus one valent tree and a q plus one valent tree. And the special question is there a surface subgroup of that G of G? So take the genus 2 surface just to fix the idea. Can I put the genus 2 surface in this product of two groups? And I didn't say with dense projections. Dense projections is free here. It's free. This is written in a paper I wrote with Larson, Spotzer, and Stover. Doesn't actually seem to be known before that, but I'm sort of leery of calling it a theorem or R theorem because it's not very hard. You don't have to do it. You don't have to assume that the surface group projects gently. That's the factors. And I'll tell you a little story about where this motivation comes from. Now, I'll pause for a story, which is that Sponsor and Stover are working on a problem not related as far as I know to this question, and trying to prove something about n-dimensional hyperbolic manifolds for high n. That was what we're interested in. We're interested in hyperbolic surfaces, and kept cooking up proofs and then having them fall apart as one does when trying to solve a new problem. And I realized at some point that everything we're trying to do would prove that I couldn't put a surface group in this product. Like, it wasn't what we were trying to prove, but accidentally, every time we wrote down a proof idea, writing down a proof idea that would prove that, I believed that very firmly at the time that was false. we're all on MSRI, so I walked downstairs, found Ian Abel, who was in the building. He said, Ian, give me an example of a surface group sitting discretely in SL2QP times SL2Q2Q. And he said, oh yeah, there are lots of those. Give me a little bit, I'll send you one maybe later tonight. Ian sent me a few emails over the next few days with ideas, none of which worked, and then sent me an email saying, yeah, I really don't know how to do that. And so I proceeded, I still thought, oh, okay, Ian may be the best guy in the world with certain kinds of things, but maybe I just asked the wrong guy. Somebody must know how to put this surface group into this isometry group of a product of two trees. And so I must have asked 100 people over the course of the next few years for the example of this that he was still basically assuming was known. The thing that sort of clinched it for me that it wasn't was, and like building surface subgroups is something people do a ton these days, right? There's the work of Kahn and Markovich, there's all this work around the Nosov representations. There are huge industries full of people building surface subgroups, Lie groups, and other groups. And you kind of think, okay, there must be a surface group sitting in here, and somebody must have already done that because there are a gazillion people building surface groups. And one day I was at this conference for Alessandro Yossi's birthday in Zurich, and I ended up after lunch having coffee with Pierre-Emmanuel Frost, Nicolas Madot, and Yves Benoit. And I asked Nicolas this question over lunch before we met the other two guys for coffee. And I talked to Frost about it like 3 or 4 times. And suddenly Yves Benoit asks us this question over coffee. And the 3 of us just laugh as we think Yves is taking the piss out of me because I must have asked him too, because I am by that point legendary with bothering me for this question. But Yves had come to the question on his own. And he's the one who pointed out to me that, okay, if you have the surface group, and he clearly knew this thing that I say is our paper. I don't think he read it in our paper, just do it. He said, the surface group is nice, but all you're using the surface group in the trees for is get the dense projections for free. Take a free group in the product, and you put a free group in a product in such a way that the projections are dense. And you make it SL2R times SL2R. Well, you can put a surface group in either SL2R, but can you put a surface group in SL2R times SL2R, where both the projections are dense? Could you put a free group in SL2R times SL2R, where both the projections are dense? He asked us all these questions. We had no idea. And I then asked a few friends these questions, and it became very clear to me, okay, nobody has any idea how to do this. I have since then found a couple of papers in the literature where they claim they know how to do one or more instances of that. Let's just say there are at least some private retractions in the world. When I push people on their claims to be able to do this, they definitely can't. It's not anybody's theorem that they can do this, but occasionally some special case of a theorem that depends on finding a free group in a product like this that has dense projections. Every time I push them, they wait, did you really do that? And we discussed it. It's turned out to happen. So it's a really odd question. That I think the entire community was assuming one answer to, and yeah, we just don't know that it is the correct answer. And so now I want to try and relate this to hidden symmetries sometime before I'm supposed to stop talking. So we have to get the hidden symmetries somehow. And to do this requires a little bit of work. And I want to actually justify it for you. Somehow we'll at least prove one of the theorems I have stated, or at least sort of able. So let's specialize in the following way. We have G be a product of 2 factors. What did I want to assume? This is just for simplicity. Everything works with the product of A factors up to adding some noise. Let's think of G1 as a Lie group. And G2, a p-adic group of, p-adic, and the important part here is that this is totally disconnected. It really has some properties in common with Lie groups and some not in common. And the really not in common thing that I want to depend on let's just pick gamma in G1 times G2 discrete with dense projections. Now we're gonna just look at it for a minute, and we're gonna use some basic facts. First of which is that there is a K in G2, which is a maximal compact open subgroup. Now, Riemannian geometers won't like compact open objects, but tough, they exist. And the example here that you should keep in mind is this SL2GP, putting an SL2QP. If I just take the p-adic completion of the integers, that ends up being compact, it also ends up being open. And for any G and G2, GK, G inverse intersect K has finite index. In K. You might look at that and be confused. This really is just. This is an open set. I can translate it around, cover this compact set. I can find a finite subcover that proves this finite index statement. So this is really just a completely elementary fact. Once you believe this is a compact open subgroup, don't believe it's a compact open subgroup, it's not clear at all. Believe me that it's a compact open subgroup. For this too, I can make an exercise. Easy points of topology. And now this is going to be a little bit too cumbersome, but it's what I want to do. What we're going to do is we're going to take a group called, we'll call it gamma 0. And what do I want to do? What I want to do is I want to take gamma and project it onto this second factor and intersect it with my compact open subgroup. The only thing I don't like about this is now this is a dense subgroup of this compact open group. We'll get its preimage back upstairs so it becomes discrete. And then we'll project it onto the first factor, because why the hell not? But we gain something here. So when this is just some dense subgroup of this compact open group. This is just look at the preimage upstairs. Projection on the first factor. This is a subgroup of G1 that is now discrete. And it's now discrete in G1 because, well, we've sort of gotten rid of all the density inside of G2. For it to be discrete in the product, when I intersect with this compact open subgroup, I better stay discrete in the first factor. That's gonna happen. So that's projection monocompact thing of a discrete thing. We always say. And then this fact here is translating this fact here. What we get is that gamma gamma 0, gamma inverse intersect gamma 0 has finite index in gamma 0 for every, well, if I want to be really careful, I'll call the projection on the first factor of gamma 1. And say for every gamma and gamma 1. And this now just factor follows from just combining this definition of gamma 0 with this fact. It's just an immediate consequence of this fact plus the definition of gamma 0. That we have finite index here, and it's actually a symmetric condition. It's not just finite index in gamma 0, it's finite index in gamma 1 as well. And that is, that property This is basically a definition that gamma 1 commensurates gamma 0. Basically, the definition of that. That is basically the definition of what it means to commensurate. And so what we have here is we have gamma 0 in G1 discrete with dense commensurator. And I would say, I'll get somewhere, but not where I want to be for this. Turns out that Greenberg and Shalom have both sort of speculated. I don't know quite how to put this, right? It's one of these things where when Shalom has never written this down. It's Yehuda Shalom and Leon Greenberg. And it's funny, this Greenberg wrote this in a paper in 1974. Shalom started asking about it in person around 2004 for different reasons. Shalom eventually learned Greenberg's work, but he sure didn't know it when he started asking. Does gamma 0 discrete with dense commensurator imply gamma 0 is loss. Greenberg only asked this for G being the isometry of the real hyperbolic space. Shalom asked it for real and p-adic Lie groups, maybe even positive characteristic Lie groups, but it's really the same question. Nobody who works in the area thinks there should be a difference between the question Greenberg asked and the rest of Shalom. They should have positive or negative answers together at the same time. So, and then you might ask, well, why are they asking if it's lattice? And it's actually kind of funny. Greenberg asking this in 1974 appears not aware of a few things. And one thing that he seems to be aware of, does seem to have known a theorem of Borel from 1960 that says if gamma is what's called an arithmetic lattice, this is gamma 0, then the commensurator is dense. And I won't say the easy special case of Borel theorem is just look at, say, SL2G. This is commensurated by SL2G. I'm not going to tell you what an arithmetic lattice is, but I will tell you that that's an arithmetic lattice, and this is its commensurator. And really, Borel's theorem is basically generalized this appropriately by defining arithmetic lattice right. And this is really, everyone calls it the theorem of Borel, but it's more of a, and I think Borel called it the theorem in the paper, but in the paper, sort of a side remark in the paper when Borel calls it, not the point. It's actually where he proved something called the Borel density theorem for the first time. There's also a theorem by Margulis in 1970. I'm going to say 74, 75. It says if gamma 0 is not of a Margulis set, is a non-arithmetic lattice, then the commensurator and so, the lattice case, and I asked Margulis at some point. So Greenberg in no way, shape, or form in his paper refers to knowing about Margulis's work. Maybe Margulis's work was done 6-8 months later, and what was then the civil union, so there's really no way he could have known. I asked Mark Lewis at some point if he had any awareness that Greenberg had been asking these questions around the time he wrote his paper, and he said, Greenberg who? Which, you know, was a little more polite, but you know, saying Greenberg who is me repeating what Mark Lewis said to me in my own voice rather than this. And so, you know, there are related things that are known. I'm going to tell you what's known about the Greenberg-Schwalm question outside of this, but maybe first I'll tell you what this has to do with hidden symmetry. Why not having told you that yet? And this, I don't know who this point of view is due to. It's a little hard to get a straight answer out of Lewis on a question like this, but I did ask him at some point if he thought of this way in the 70s, and the answer was more or less no. But he was thinking of commensurator and sort of the algebraic way I was talking about it. But it turns out if I have manifold M, which is G mod K mod gamma 0, and I would say there's some other gamma in G commensurates gamma 0, this is equivalent geometrically to there are just two covers M prime and 2M prime and 2 primes of M, where gamma gives you an isometry between. So maybe I should recall some facts, at least verbally. Think of this G mod K as hyperbolic plane. You know, it's a much more general locally symmetric space, but we don't need to worry about that. Just think of it as a hyperbolic plane. I have some hyperbolic manifold. And I'm saying what I'm saying is, okay, if there's something in the commensurator of fundamental group, then it's not an isometry of that hyperbolic manifold. In fact, all know that hyperbolic manifolds have finite isometry groups, at least if they're compact, and in fact, much more generally than that. Yes.
Do you mean the group generated by gamma commensurates gamma naught? Because you were saying a group commensurates.
Okay, but really I define it one element.
Oh,
To say the group commensurates is the same as saying each element of the group commensurates.
okay.
Yeah,
Okay.
sorry.
Okay.
So this is you know, I can't find very many isometries of M, but what's saying that gamma 0 has dense commensurator says there are really a lot of isometries of covers. You know, so the upshot is that if gamma 0 is commensurated by gamma 1, which is dense, then there exist a lot of surprising symmetries of covers of M. That's really what this commensurator condition means geometrically. And you know, this shows up in various forms in various parts of mathematics. I mean, the theory of Hecke operators and the theory of modular forms is basically built out of these symmetries. That's what they're doing, is they're looking at isometries of covers that they turn into correspondences on the original map. So we can, and maybe I should say, I'm running longer than I thought, and I've stated no theorems. So I'm going to say one thing that I plan to write on the board with quantifiers, or I'm just going to say it verbally. What does it mean to have dense commensurator? It means on my manifold M, and let's say I'm assuming that Greenberg and Schwalm are wrong, and so gamma 0 is not a lattice, so manifold M is some infinite volume manifold. It's a really big manifold. I pick 2 points on it, and I can even pick 2 points and 2 tangent vectors on it. And then there's some cover Or if I pick two pre-images of those points and tangent vectors, there's now an isometry that moves this one to that one. It seems like a really weird thing to expect from an infinite volume hyperbolic manifold, at least to me. Which is at the base of it why I kind of believe that Greenberg and Shalom are that might make this conjecture. They both sort of indicate they answer yes. And I think they're right, because I can't imagine having this kind of hidden symmetry for hyperbolic manifold. Just doesn't make any sense to me. So I'm going to use some of my question period to tell you what's known about this, which is not a whole lot. And this is where the answer to Tracy's question comes in. So what's known on Greenberg Shalom? The first theorem is with Greenberg. You just write the paper about questions. He said that if G is SL2R and gamma in G is finitely generated, then dense commensurator implies lattice. It's a nice enough theorem. Finitely generated really matters here. And for a group that's commensurated by another group, commensurator is finitely generated isn't the most natural assumption. And in particular, if you play this game that I've implicitly played through the talk, where you take this example for Linden and Ullman, you view it as a lattice in the product, and you push it back down to another discrete group with dense commensurator. If you do that with a Linden and Ullman example, there's absolutely no way to verify that the Linden and Ullman example gives you a finitely generated group. So it's absolutely not the case. Greenberg did not unknowingly prove this Linden and Ullman question. Didn't do that because of the finitely generated assumption. Another finitely generated theorem, which is somehow the second best, or one of the best results here. NJ building on Leininger, Long, and Reed. Gamma and SL2C finitely generated. You get the dense commensurator implied lattice. And once it implies lattice by Margulis, it implies arithmetic lattice, but I haven't told you what that means, so I won't bother you too much about that. And sort of the only theorem I know of without this finitely generated assumption that says anything clear about this is this that says if I have this gamma 0 sitting as a normal subgroup of gamma sitting in my gamma 1, where gamma in G is lattice, then gamma 1 dense commensurating gamma 0 implies gamma 0 is sitting in gamma of finite index. So you can take a subgroup of a lattice, normal subgroup of a lattice. And I should maybe again, I'm way over where I wanted to be for time, so I'll say the next thing verbally. If you just change this from normal subgroup to just subgroup, we can't prove it for one thing, and the second thing is that it becomes not quite equivalent to, but equivalent to many special cases of a famous conjecture by Margulis and Zimmer from 1978 or so. So that was really the thing that brought Shalom to this question, is the fact that in some cases this conjecture of Margulis and Zimmer becomes related to this question that really was due to Greenberg, but Shalom didn't know that. And the other theorem I'll state, and the theorem, just because I want my other co-author's name on the board at some point, especially because he's a young postdoc, also with the same authors, but also with Nick Brody, who's a student of being able to now a postdoc at UC Santa Cruz, is just that. What is this? How do I ask that? Yes, on Greenberg Shalom implies no, or wait, yeah, no on Linden Holman, which is also yes on comparative kin. Comparative kin conjectured a negative answer to the question of Linden. And so, and this paper is also replaced, in doing this dance for you today, I went from some random dense group of one group to a discrete group in a product, asked you a few things about discrete groups and products. This paper also sort of spells out that connection to discrete groups and products and groups with dense commensurate, which also was not previously in the literature. And along the way, we point out that there are a bunch of other applications to resolving all this to a variety of questions in group theory and geometry and topology. But if I tried to put all that in an hour, I really wouldn't have got where I wanted to go. So I'll stop there.
I got one way back at the very beginning. This sort of all spun out of the S equal rational case. You talk about the S equal transcendental case. Is anything known when it is irrational but not transcendental?
So nothing's known, but if you kind of the machinery for translating it, let's put it this way: if you had a positive answer to Greenberg Shalom, you could answer basically all cases of that, because you'd just be picking S to live in some other number field, because it's not transcendental, so it's algebraic, so it lives in some number field. You play the games I've been playing, replacing Z and Q with number fields and their integer points, and playing the same kinds of game would almost completely resolve the question, up to the case that is basically Egel's case, where I don't know if it's known, if you're actually, there's some cases left that are sort of analogous to Egel's case where I don't know whether they're known or not, because it becomes questions about three manifold groups that I don't know the answer to. But up to those, the same machinery, if it could answer the question, would answer the question completely.
And Hegel gave complete description when a discrete group free, or what did he do in this?
So when you're looking at one of these gamma sub S's, and that gamma sub S is discrete, he told you what the group generated by those two matrices is. And they turn out, I believe, in all cases, of which there are only two or three, and maybe he actually did the answer to that part of Greg's question too. I'm not sure, I don't remember off the top of my head. They turn out to be break groups. Like, he describes explicitly what group these two matrices generate. He writes down a presentation of that group and tells you exactly which group it is, using knot theory and true manifold techniques.
Is he one of the seven authors?
No, he is not one of the seven authors. If you knew him better, you wouldn't ask.
So, do you know at least one author to find this out?
I can find it for you. I don't actually have to top of my head. No. If I knew any of the seven authors, I'd do the embarrassing thing of telling you the names I know, which would be, it's just always awkward, but I can find it for you.
Any other questions for our speaker? All right, well, let's thank the speaker one more time.